So welcome to lecture 19 of our CT6 CS2 classes. And this is probably the last topic that I'm going to teach you. So this is called time series. And I think you all must have encountered time series in a way or the other. Can I have an example from each one of you about, what do you think a time series would look like in any field?
An example would be stock market prices that we watch.
Yeah, so stock market prices that we watch, and we know that when recorded over some particular time period, right? So whenever
Yes.
we try to define a time series, we have to keep certain things in mind when we define a time series. So if you were to define, let's say, the stock market series, you would say, the annual returns from a company that you might care about, or the daily returns, basically, not even annual returns. So that might be one of the time series data, or the price of the stock as well. Rishabh?
We can see a balance sheet of a firm. It can be a time series. If we are calculating it daily or
What did you say?
if we are calculating it daily, a balance sheet or some account of a firm, a bank account.
Okay, yeah. So maybe we want to take only one aspect of one particular of the balance sheet, not the whole balance sheet, right? Maybe the profit or the investment in the shares over a period of time, right? That would be the interest to the stakeholders of the company. That's a good example. Sakshi?
Ma'am, I'm still thinking.
Okay, no problem.
Ma'am, it could be daily weather data.
Yes, it could be daily weather data. That's nice example as well. So you can record the temperature, in a city or a town. That's good. Or you can even see, the chance that it rains heavily and floods and all the sort of stuff based on the temperature. Okay, that's good. Sakshi, have you thought of some example?
Air quality.
Air quality, yes, it can be air quality. So maybe one of the parameters to measure the air quality must be the air pollution that's there, right?
Yes.
So you can maybe plot the levels of the pollution in whatever terms it's measured in over some period of time that is of interest to us. Exactly, right? So each of these examples that we just saw, what they do is they track a single metric, right? There is one single quantity of interest that particularly is of importance to us as an analyst or a researcher. And what we see is we observe that particular metric at some regular time points, right? And that so the data that you have is known as a time series data in that case. So there are other kind of data as well. You can get the panel data, you can have cross-sectional data. So let's say when you're talking about cross-sectional data, you don't care about the time aspect. You only care about, the quantity of interest over particulars. So let's say you're looking at the pollution by the households, by energy firms, by banks, and you can have a data set for that. And let's say if you're looking at the panel data, then what you are doing is you look at the data over time and along all the different stakeholders that you're looking at. So in the energy case, it would be across all these sectors and at different period of times. But in time series, what you do is you only take into consideration the time aspect of it. Have I shared the screen? Yes, I have. Okay, so we take into consideration the time aspect. So there should be a fixed time interval at which you are recording your data. And that is when you observe the data basically. And the other thing is that you are only caring about a single metric, because what we are going to study now is a univariate time series, and which is why you care only about a single metric now. So there will be multivariate time series. I guess we have that in our portion. But yeah, for now, we're going to focus on the univariate time series. And I think whenever as a researcher, you're trying to, you have a question in your mind and then you try to understand, let's say, some patterns in the changes over time in whatever quantity that interests you. You know that you have to model these patterns, right? For various reasons. You can just try to model this to see how a quantity behaves over a period of time. You can try to model this, just to see how it could behave in time. So maybe you want to forecast and predict what is it likely that we are going to observe for a particular data set. And otherwise, it just helps us to understand better the environment that we live in or the quantity that interests us as a researcher. So if we go on to the exact definition of a univariate time series. So what we're studying is a univariate time series. To define this in statistical or, the pedagogical terms, I would say that a univariate time series is a sequence of observations. So we know that we are observing some sequence of some process taken at a sequence of different times. And for our considerations, we are taking those times to be fixed intervals as well. So generally you denote this as xt1. So this would be the first observation that you have, and then xt2, and so on till xtn. So this is the n times that you have observed the data that you have at hand, right? And this is how it is in mostly all the applications. So remember, all the things that we studied up until now, the data that we looked at in, let's say, the reinsurance chapter or the copula or extreme value theory chapters, what we saw was that the data is generally independent and it is identically distributed as well, right? But for this time series data, remember that these are never independent. And that is the whole reason to model them, because as analysts, what we want to try to do is we want to figure out the kind of dependence that there is, and that is what we have to recognize and exploit from the data that we have. So the goal is to model the changes in the metric that we are looking at, which is the dependent variable here. And the independent variable would of course be just the time, because we know that time is independent, it doesn't really depend. So that's a way to, look at a time series. And so when I'm talking about fixed time intervals, in the case of univariate time series, I can discard the writing of these kind of types, and I can just go on and ignore that t and write it as x1, x2 till xn, where I know that, my t takes values from 1 till n. So this is basically my xt. Does this make sense? So this is just a notation bit of it, I would say. Not much to understand here, but that is just to, see how we are going to write it out. Okay, so now we know that there can exist two types of data, mainly discrete and continuous. So if I were to categorize the variables that I have in my time series, one is time and the other is the metric that I'm looking at, the characteristic that I want to, figure a pattern in maybe. So when I talk about time, I know it can either be discrete or continuous. So let's say if I'm looking at the stock price data, which let's say if I'm looking at the daily stock price data, then that would be a discrete time interval. But if I'm looking at the continuous returns that I get from a stock, then that could be the continuous time, right? And if I'm looking at my data as well, it can either be continuous or discrete, but generally it is continuous because let's say if I'm looking at the stock price itself, the price can be anything, right? 26, 26.4, 10, any number. So generally what you say is, for our actuarial purposes, we'll be looking at discrete time, but continuous state space. So the time that we are going to look at is discrete. We will know the exact intervals that we're going to look at, and the data that we are going to map is going to be in the continuous space. And also there is, I think you all have already studied CT4, I mean, the first part of the CS2, which talks about stochastic processes. So can someone tell me, how do you define a stochastic process? Anyone? How do we define a stochastic process? Like, what is a stochastic process?
Any process with a random variable.
That was a nice answer by both of you. Okay, so any time dependent random variable, right? And here what I'm looking at is x1, x2, xn. And this is just the time, right? 1, 2, and n. These are the times that I'm looking at. So I can say that my time series is a stochastic process, right? Because it, of course, depends on the time and it varies across times. So a time series process is a stochastic process indexed in discrete time and continuous state space. And when I say continuous state space, that is just the values that my process can take. So that would be the values x1, x2, and xn. Good. And okay, so there is another concept of, a doubly infinite collection of time series. So when I talk about time, what do you guys think should be the starting point of my time? Like the starting integer that I should denote my time with. Should it be 1 or should it be 0 or can it be in negative? What do you guys think? Can it be 0 or can it be negative?
0.
0.
It
And
can be
negative?
negative if we think in terms of relative purpose.
Yeah, it can be negative as well. So this is a fairly new concept. So we know that time, when I'm looking at time, as I said today, so I'm looking at something from today onwards. So if I start today, I'm at 0 time interval, right? And let's say if I look at 1 year ahead, I can write as +1. But if I want to look at something which has already occurred, then I can maybe claim it as -1. Maybe it does not exactly mean that the time was -1, but just the fact that I can denote it for my purposes from where I'm standing today as -1, just to have a look at, what happened the year previous to today. So this is just a relative concept. And you know that if I give you time, let's say if I write 1996, 1997, 98, 99, and blah, blah, blah. So if you're looking at, so let's say if you're here today, then you can always say that this is -1, -2, -3, and that is 0, right? So it did not mean that the time is -3. It just means that this is how you are denoting time. And this is exactly what you're looking at. So it depends from purposes to purposes. And what you now can say is, whenever I'm looking at this time interval, so I'm looking at something which goes from 1 to n, right? This is nothing but just a subsequence. So we know that this is the sequence of the time intervals. And if I'm looking at something from -infinity to infinity, then I will say that this is just a subsequence of a doubly infinite collection, which I denote it as this. So it can go from 1, 2, and so on. So this is just one subsection of this whole sequence that is there in actual. So you only pick out the part that interests to you or that you're interested in, and you can, and again, let's say if I have -3, -2, -1, 0, you can again put some proxies to this as another time, which is 1, 2, 3, 4. It wouldn't really make much difference, but you have to keep in mind and remember how you proxied this time. And that is just to suit your purposes and just to make your calculations easier and not much of messiness to be in there. So this interpretation that we just saw, I'll use in some another concept that we'll have a look in a while. Okay, so have you guys heard of stationarity before?
Yes.
What do you think it means?
The statistical properties do not change with time.
The statistical properties do not change with time. That's good. What about anyone other? Do you guys have any other idea that can define the stationarity? Anyone? I'm looking at stationary.
The proportions remain same as in Markov chain. The stationary, the proportion remains same.
Can you say that again?
As in Markov chain, the proportions remains the same, so that is also stationary distribution.
Okay, yeah. So that is just one example of how things can be stationary. Good. So when I'm talking about stationary in general in English, so in English, what does stationary means? Jahan par hai wahi par ruke ho, right? You aren't moving anywhere. You are where you were and where you are going to be. So that just is the English definition when I talk about stationary something. And the same concept has been applied in statistics, and that is why we have the name stationary, is because the statistical properties over a period of time remain unchanged for some data set that we're looking at. And that is when we say that, the process which describes that data is a stationary process. So if I were to define stationarity, you have two different kinds of stationarity. One is strict stationarity and the other one would be weakly stationarity. And when I talk about strict stationarity, what I mean is, so let me just write it down. So this is generally very difficult to observe, but still we need to know what it means when we talk about strict stationarity. It means that the joint distributions, so when I'm talking about the joint distributions of xt1, xt2 till xtn and x t1 plus k, comma, x t2 plus k till x tn plus k. So when I'm talking about these values and these values, so we can easily see that the only difference that lies is that I have an additional k here. I have an additional k for all the points that I have written in this second bit of the series that I'm looking at. So when I'm talking about strict stationarity, what I mean is that the joint distribution of this series and this series, which is just, indexed at some k time period ahead of this one, are identical. So these should be identical. The distribution for both of these processes should be identical for all the time periods that we're looking at. So, yeah. And again, remember, whenever we talk about a time series, time is of utmost importance. So although I can write in my doubly infinite series as, -3, -2, -1, But for our purposes, we incorporate the fact that time flows only in one direction. And the past events that we have can influence the future observations, but not the other way around. And we'll have a look again that, how if we have a look at the close observations, then we see that there is a stronger association than when we look at the observations which are farther away from the time that we're considering now. So we'll discuss that later. And let me just now discuss what do I mean when I talk about the weak stationarity. So as the words suggest, strict and weak. So when I talk about strict stationarity, a process which is strict stationary need not be weakly stationary, but any process which is, so any process which is strictly stationary will always be weakly stationary as well. But any process which is weakly stationary need not be strict stationary. So if I were to write, so if we know that something is strict stationary, it may or may not be weakly stationary as, it will be weakly stationary. And when I'm looking at weak stationary, it may or may not be strictly stationary. So how do we define weak stationarity? And that is just, a matter of saying that the mean remains constant over time. So the mean is constant. This is one condition. The another condition is that the variance is constant. So when I'm talking about the mean, I know that I can rewrite it as expectation of xt. If I'm looking at some variable x, right? And then when I'm talking about the variance, I can just claim that my variance for some process xt is sigma square. So remember, you will never have these p subscripts here. These are not allowed because what we are looking at is a time series, which is weakly stationary. So this is something that you should avoid. Okay, and the last bit is that the covariance. Okay, so if I, let's say, have two random variables, x and y, and I'm figuring out the covariance between them. It's just called covariance between x and y. But let's say if I'm looking at the covariance between x today and x tomorrow, that I can claim that I'm finding the dependence structure between the same variable today and the same variable day after. So I can say it as not only covariance, but autocovariance, because I have the same variable into consideration. But still for this purposes, I'm going to write it as covariance. So the covariance depends on lag and is independent of t. So t is the time that we are looking at. So let me just have an example. So let us say we are looking at the covariance of xt and xt plus t. So do you guys know what do I mean when I talk about lag?
Yes.
What is lag? Yeah, you all know, right? So the lag here is just k. So I'm looking at the difference between t plus k and t, which is just k here. So I know that if I'm saying that my covariance should depend on the lag, so my covariance should be k. Do you guys agree with this? When I'm saying that my covariance should depend on the lag, and I know that my lag here is k, so if I write this covariance as k, is that okay?
It should be a function of k, I guess.
Exactly right. It should be a function of k. I haven't said that my covariance is the lag. I have just said that my covariance depends on the lag. So it can be any function just with the variable, which is the lag, right? And we know that the general formula for covariance, so the function that I have denoted here is this gamma, and that k is the lag. So that holds for all k basically. And if we just use the general covariance formula, what we would have is expectation of xt, comma, xt plus k minus the expectation of xt times the expectation of xt plus k, right? So that is how I can define my covariance that I'm looking at. Do you guys understand what I'm talking about?
Yes.
Okay, I take that as yes. So we'll try to say, and this actually holds true, why. I'll tell you why. So whenever I have a normal distribution, so let's say if I'm looking at, a random variable which is normally distributed, then if it is weak stationary, if the process is weak stationary, it will always be strict stationary as well. And why is that the case? Because so we know that for strict stationary, we want the distributions to be identical, right? And when I'm talking about normal random variable, its distribution is determined by the mean and variance. So if you know the mean and if you know the variance, you can easily determine the whole distribution that a random variable follows. And so what I've assumed is that my random variable is weakly stationary. So it means that the mean is constant and the variance is also constant, right? And that is what defines the distribution as well. So you see, it's really intuitive to say that if you are looking at a normal random variable, and because it is completely determined, by the mean and the variance. So when I talk about variance, I'm also including the covariance, because let's say if you're only looking at two random variables, you will have, let's say, x, y at t and at s. So here it would be the variance, here it would be the covariance, again the covariance and again the variance. And you can have similar expansions. So this kind of matrix that you get is generally known as the covariance matrix. So this is also the covariance, but just with the same variable itself. So I think it's fine. Yeah. So when I'm talking about a normal random variable, and if it's weakly stationary, then I can easily say that it is going to be strictly stationary as well, but never in any other cases. Okay. So now when I'm talking about weak stationary process, there are so many processes in this world which can be weakly stationary. But then, so let's say if I give you an example, if I write some sequence, which is just this, or it is just this. So this is my value for x1, and that is my value for x2, and that is my value for x3, and so on. So these are the series which we know have constant mean. Okay, not maybe this, sorry. Let's just take the upper example. So we know that this series has a constant mean of 1 at whichever time we look at, and it will also have a constant variance, and it also has covariance, which is independent of time and dependent only on the lags. So this is also a weakly stationary process, right? But for our time series purposes, so you do not need to have a model to predict what's going to happen next in this case, right? So the kind of processes we look at have to be indeterministic processes. So there is a term known as purely indeterministic processes, and that just says that, as and when you move away, as and when you move, let's say, ahead. So let's say if you have the data from x1 up until xn. So you have so much of data with you, and as and when you try to predict the values of ahead, these values decrease in their importance. So they're less and less useful in predicting the values which are ahead as n goes to infinity. So whenever from this time onwards, whenever I'm going to say that we're looking at a stationary time series process, what I mean is that I'm looking at a weakly stationary, purely indeterministic time series process. I think maybe I should just write it here. So we are looking at a weakly, purely indeterministic time series process. Let us now try some examples, maybe just to, fix it in our mind about the concepts of stationarity. So let us start with an easy example. Let's say I have xt, which is just equal to xt minus 1 plus yt. And when I'm talking about these, I say that my yt is a random variable, which is a sequence of independent standard normal variables. So we have to determine if xt is stationary. And when I say stationary, I mean weakly, purely indeterministic stationary kind of a process. So what do you guys think I should do first? Check its mean, right? If it is constant or does it depend on time? So to check its mean, what I can do is I'll have expectation of xt, which will be expectation of xt minus 1 plus yt. And I know that these are independent. So it will just be expectation of xt minus 1 plus expectation of yt. And I know what about yt? I know that yt is a standard normal random variable. So the mean is always 0. So this is going to be 0 in value. So the expectation of xt is just equal to expectation of xt minus 1. So what do you guys think about this? What does this mean?
It is a weekly. We have to find variance also.
Yeah, we have to find variance also, yes. But what kind of a mean this is? Is this a constant mean process or is it not?
Yes, it is constant.
Right? Although we see that there is time subscript here, but try to remember that we have an expectation here, and I'm looking at the expectation of x at today, which is just equal to the expectation of x yesterday. So that clearly says that if I'm looking at expectation of xt minus 1, then that would be expectation of xt minus 2. And by transitivity, we know that all of the expectations are equal. So we know that there is constant mean. Perfect. Now let us look at the variance. So I have variance of xt. And I just substitute in this. So I have xt minus 1 plus yt. And again, because they're independent, I'm just assuming that the covariance is going to be 0. So the variance of xt plus 1 plus the variance of yt. And because standard normal, this is going to be equal to 1. So what I have indeed, in fact, is variance of xt plus 1 plus 1. So what do you guys think is going on here?
The variance is not constant.
It is increasing by 1.
It is increasing by 1, right? The variance is not constant. So let's say if I'm looking at variance of xt, it is variance of xt plus 1 plus 1. But if I would have variance of xt plus 1, it would be variance of xt plus 2 plus 1. And then if I compare variance of xt and variance of xt plus 2, then there will be some differences of 1, right? So this process is clearly not stationary. So this right here is not constant. Perfect. And let us
It
look at
should be
another.
variance of like xt minus 1.
Oh yeah. Okay, yeah. Yeah, sorry. Xt minus 1 everywhere. Yeah. Oops. Thank you very much. Okay, so let us look at another example. So now I have my xt equal to some 2 plus 3t. What do you guys think this could be? Will this be a stationary process?
No.
Right? You can easily see that we have this term here, which is 3t. So if you take its expectation of xt, it's going to contain a term which is 3 times expectation of t, which is just t. So the expectation is going to depend on t. That is why this process is not stationary. Okay, good. Let us look at another example. This is a bit of a nice example. So I have my xt as yt minus 1 plus yt. Okay, so what should I do first? The expectation, right? And if I were to calculate expectation of xt, it would just be expectation of yt minus 1 plus expectation of yt, which is 0 because both of these are independent normally distributed, standard normally distributed. Cool. So now if I were to calculate the variance of xt, what would that be? It would just be the covariance between yt minus 1 plus yt and yt minus 1 plus yt, right? We know that this is independent of that and this is again independent of that. So we would again only have variance yt minus 1 plus variance of yt. The covariance term would just be 0 and that would again just be 2. So it is a constant, right? Good. And now we have to look at the covariance as well. So remember, I can write my variance of xt. So when I'm looking at variance of xt, I can rewrite it as covariance between xt and xt plus 0, right? So if I'm going to compare this with my covariance formula, so I'm figuring out the covariance between xt and xt plus k, I can easily say that if my k takes a value 0, my variance of xt, which is just the covariance of xt comma xt plus 0, is always 2, right? It is always 2?
Yes.
Okay. So let us say now if I'm looking at lag 1. So let me consider the case where k is 1. So what we need is that my covariance should not depend on time, but only the lag that I'm looking at, right? So if I were to figure out this covariance of xt, comma, xt plus 1, what can I write it as? I can again just expand my xt, yt minus 1 plus yt, and xt plus 1 will be yt plus 1, right? And now I know that this is independent of this and that again, and there's only one term which matters here is yt and yt. So this would be just the variance of yt, which is what? Just 1, right? And just for a change, let us look at covariance of xt minus 1, comma xt. What do you guys think the value of this should be?
Zero.
0. And why do you think it should be 0? Yes, Sakshi.
I think it's going to be the with the value of k. No, it should be 1, I guess. It depends on the value of k.
Okay, so let us try to figure out what this is, okay? And using our usual thing, we have xt minus 1. So we would have yt minus 2 plus yt minus 1, comma. And for xt, I can write yt minus 1 plus yt, right? And if I just equate it, this is going to be independent of that, and we only have these terms. So this will be variance of yt minus 1, which is what? 1. So you did confirm that whenever there is lag of 1, so whenever we are seeing a case where k is 1, so what is k? How do I determine what is k? Not exactly by seeing what is the coefficient with p here. I determine my k by looking at the difference between this and that. So here if I look at p minus t minus 1, it's going to be 1, right? So again, I got my answer as 1. So maybe what I can write now is that whenever I see a lag of 1, my covariance value is 1. So k, whenever is 1, the value for my covariance is also 1. And also try it with having xt there and xt minus 1 here. So you know that, it will just be this the other way around, but you will still get the same answer. So what you can do is you can put a modulus here. So for all the absolute values of k as 1, you get the covariance as 1. And would someone want to guess what happens if I have an absolute value of k as 2? What will
be
happen
0.
in that? It will be 0. Why?
Because there will be no relation between the variables inside.
Yeah, right. So let me just write it for a while here. If I'm looking at k is equals to 2, so I'm looking at instead the covariance of xt, comma, xt plus 2, right? And if I expand my xt, what I get is yt minus 1 plus yt. And if I expand xt plus 2, what I get is yt minus 3 plus yt minus 2. So you see t minus 1, t minus 3, t minus 2. So there is no common term, and we know that these are independent, so it's going to be 0. So we know that the value here is going to be 0. So, and even if you expand this 3, it's just going to decrease. So what I can instead say is, not only for my absolute value of k being 2, this is 0, but for any value of k which is greater than or equal to 2, my covariance takes only one value, which is 0, right? So what do you guys think? Is this process weakly stationary or not?
It is weekly stationary is confirmed.
Yeah, right. So because we know that the mean is constant, variance is constant, and the covariance depends only on the lag, right? Which is also again constant. So we know that. So see, the covariance has no t term in there, and thus we can see that this process is indeed a weakly stationary process. So it is a weakly stationary process. Again, we see that some processes are stationary, some processes are not stationary. So whenever you observe a random variable and whenever you observe it at a fixed in time interval, and it turns into a process, you can sometime have with you a process which is not stationary. So the very first thing that you should always come to your mind is that, let me try to see if the difference is stationary. So this generally happens in the case of price and returns in the stock price. So as we know that we never generally study the prices of the stocks. What you study more is the returns of the stock, the log returns of the stock in particular, right? So that is why, because the returns are stationary, prices need not be. And what is return? Return is just the difference between the prices, right? Divided also by the base price, but it is more like just the difference between the prices. So whenever you encounter a series such as price, which is not stationary in the first place, you try to take its difference and you try to see if that is stationary. So let's say if you have a process X and it is not stationary. And this process is not stationary. So what I do is I take a difference and then I get another process which is stationary. So I know that if I claim that there is another process Y, so I should maybe write the T subscripts, which is just the difference between these, and this is stationary. So what you will do is you will work with these data, right? And you see that my YT is stationary, which is just the increment in the X. And there is some term that you denote it by. So whenever, let's say if you have a process XT, which is stationary, you say that this is an integrated process of 0. So this is integrated and this determines the order. So when I write I0, it is read as integrated of the order 0. So if I have a process which is already stationary, I say that it is integrated of order 0. But when I have a process xt, which is not stationary, but its increments which are stationary. So I had to difference it once. And in that case, I will say that this process is integrated of order 1. And so on. So let's say even if you do this difference and yt is still not stationary, so what you will do is you will have another random variable, let's say zt, which is yt minus 1. And if that is stationary, then you say that x is an integrated process of order 2. It should be of order 2. So that is how you have to care. And when we look at the models, you will have a look that there are different kind of models that you can have in a time series, and how does this play important role. Next. So let us start with the autocovariance function. So there will be some terms and some preliminaries that we should all be familiar with before we start off with studying exactly what we have in the time series. So what we'll try to do is maybe just start off with the autocovariance function. So this is the covariance with the same random variable, just at different times. Covariance function. Okay, so I can just write that this is my covariance of, let's say, xs, and x at time t. Then that would just be expectation of xs times xt minus expectation of xs and expectation of x at t, right? So Again, do you remember how did I denote? So let me just, instead of T, write let's say we have xt and xt plus k. Right? So this is my covariance of xt and xt plus k. So, and again, just to remind you guys, always whenever we are working something, whenever we use our statistical functions on any time series, we make sure that it is stationary. So that is the primary condition that we need our processes to satisfy. So we know that the covariance should only depend on the lag if I'm looking at a stationary process. So I denote this covariance where I'm looking at the lag k as gamma k. Is that clear? So I denote this as gamma k. So that will be my gamma k. And as and when k vary, your subscript to that gamma will also vary. And if I'm, let's say, looking at the covariance of xt and xt, how can I write this as? That will just be gamma with subscript 0, right? Because, and that is just the variance of xt. So remember, when I'm talking about the variance, the subscript is always going to be 0 because there is no lag in it. And I'm looking at the dependency among the same variable at the same time period as well. So that's the case. And we'll have a look how does this value of autocovariance helps us to determine what kind of model should we use, to approximate to the data that we have at hand. So, and I'm just assuming that you all know the rules of covariances, right? So if I'm taking a covariance of, let's say, x and some number 2, what will the answer be? Anyone? 0, right? Because it's just a constant that I have on the other side. And let's say if I'm looking at covariance of x and y plus z, how can I rewrite this?
Covariance of
Again,
xy and plus covariance of xz.
right? Okay. Right. And let's say if I have covariance of 2x and 5y, what will this be? That will just be 2 times 5, the covariance of x, y, right? Because whenever we talk about variance of, let's say, 2x, 2x, so covariance of 2x, 2x, which is just the variance of 2x, what I get is 2 square times the variance of x, and this is where you get the square from. You multiply this 2 and that 5. So I hope you all are aware of the general properties of the covariance. If not, there is a simple exercise in the book, and you can, just remind yourselves of that. Okay, so now we have autocovariance function, but as we know, autocovariance will depend. So let's say if I'm measuring the stock price, and if I, let's say, determine the autocovariance function for that series, what will I have? I'll have some number and the currency attached to it. So let's say if I'm looking at rupees, if I'm looking at some Indian stock price, so I'll have some rupees squared attached to it as the unit. So what we generally do is to make it, a dimensionless quantity, which is easier to compare across, I'll just calculate the correlation. So here, if you're looking at the autocovariance, then if I'm looking at the correlation, what I will call it is the autocorrelation function. So that will just be autocorrelation function. Anyone would like to guess the formula for autocorrelation function? It is going to be the same as in general that you have for the covariance, for the correlations. So let us maybe try to write that. So if I'm looking at the covariance, sorry, we're talking about correlation. So if I'm looking at the correlation between xt and xt plus k, my formula for this would be what? Covariance among this upon the square root of variance of xt times the variance of xt plus k, right? And again, we know that we are working with stationary series. So what I have here is variance of xt and variance of xt plus k. And I know that they are going to be the same value, right? So this is going to be equal to the variance of xt plus k. Which I can denote as gamma 0, right? So I can just rewrite this as, so this is my covariance. It will just be my gamma k upon square root, and this will be gamma 0, and that will also be gamma 0. So what I have is gamma 0 squared, and I can just rewrite this as gamma k upon gamma 0. So that is how I define my correlation function. And I will denote my correlation function with rho, but we have to keep in mind the lag that we are looking at. So the subscript will be k. I hope this is clear to everyone. Okay, so just let's say we are looking at normal random series, or normal random variable, and we have a process that we have observed at some regular time intervals, the process. And let's say if I want to, let's say if I have the data from x1 till x10 and of the stock price of some company, and if I have to figure out what could be my stock price at x12 and at x20. So I know that the data that I have is only till x10, and it is more likely to be accurate for the prediction of x12 than it would be serving the purposes to calculate the x20, right? And when I look at the correlation as well, I know that as and when I increase the time period, the future time period, when I'm looking at the data value, I know that as and when my lag increases, the correlation among the starting date where I am and the date where I would be after that lag taken into consideration, that would be lessening in value as and when I increase my value of k. So we can say that my correlation for lag k goes to 0 as k goes to infinity. So this is just another fact that we have for at least purely indeterministic time series. Okay, so I think you all have already studied white noise processes, right? Have you guys studied white noise processes?
Yes.
Can someone define it for me? What is a white noise process?
A discrete time stochastic process of independent variable.
Of independent variables. Okay. And what are the properties of white noise process? So let's say if the variable I'm looking at is ET, the error term generally. So they should be uncorrelated, right? The variables that I'm looking at, they should be uncorrelated. So white noise process is actually just a simple example, the very primary example of a weakly stationary random process. So let us say I'm looking at my ET. This could be the error values and where my T is any integer. So this is the random variable that I'm looking at, and that would be white noise if my expectation of this is 0 and if the covariance. So I know that this should be uncorrelated to each other. So let's say if I'm looking at E today and at E someday later, then it should have the value of 0 for k greater than or equal to 1 absolute values. And if my k is 0, it can be the variance, which is just constant, but shouldn't be dependent on the time. And again, I can rewrite this as just gamma k. So this is actually a very important white noise process. And yeah, generally we know that, errors are normally distributed. So if we know the mean and if we know the variance, we know that we know the whole distribution of these errors. So yeah. And again, this mean need not be 0, just some constant. But in our case, we are assuming that it is 0 as well. That is just one peculiarity. And we have already studied. So when we studied about the covariance properties, we know that I can actually say that my gamma k is equal to gamma minus k. Do you guys agree with that? Let me maybe try to prove it. So maybe we can do it here. So I'm looking at a proof of the fact that gamma k is equal to gamma minus k. Do you guys think you can do this on your own? Let me try to share the book. Okay, so if I'm looking at the covariance between xt minus k, between xt and xt plus k. So what we have is gamma k, which is just covariance between xt and xt plus k, right? And we know that it shouldn't depend on t. So what we can do is, we can have covariance of xt minus k and xt minus k plus k. So that would again still be gamma k because we're looking at the difference between this time and that time, and that would be this k right here. So this would again still be gamma k. And if I were to rewrite this, I can cancel this k k's, and I'll be left with covariance of t minus k comma t comma xt, and which will be equal to the covariance of xt comma xt minus k, which I can just rewrite as gamma minus k. So when such kind of so we have gamma k equal to gamma minus k, and thus we can see that this gamma is an even function. So if I know that my gamma is even function, I know that my autocorrelation, which is denoted by rho, is also an even function. But that is just, that is just a nice result which you can use to figure out the negative lagged values when you know the positive lagged values for the same lag. Okay, so now we'll have a look at, various kinds of time series, the typical time series that you observe. So whenever I'm looking at a time series, let's say if it is some economic time series where I'm looking at the inflation rate. Oh, so do you guys know how is the inflation generally measured across the countries? This is a really nice thing. So what they do is they see the price of the McDonald's Big Mac, and that is what helps them to determine the inflation and compare the inflation amongst different countries. Like that is maybe too into economics, but that is really an interesting thing. So now, okay, so we just studied about correlation, right? And we know that the values of correlation that we can have can only be somewhere between -1 and 1. It can never go beyond -1 and beyond 1. So the graph where you plot these autocorrelation functions are known as correlograms. That's just some nice word. Okay, so let us say I want to figure out my rho at lag 0. What will it be? It just means that I'm looking at my covariance of xt, comma xt upon gamma 0, and this is also gamma 0 upon gamma 0, which will just be 1. So we know that irrespective of any time series that I'm working with, the value for autocorrelation at time interval 0 is going to be 1. So that's the case always. And you just get different values, for different lagged here. And that is how you will see and determine what kind of a process this is. So if you look at this particular graph, you see that the correlation value has decreased and it became 0 at the lag 3. So for lag 1, there was still a bit of correlation. For lag 2, it has decreased a bit. And for lag 3, it's suddenly 0. So it has decreased very quickly and gone to 0. So we know that, there is no correlation after lag 2 in the series that we are observing. So this series actually is nothing but just this. Where this, so this is En, and that En is just so this was the thing that they plotted up there, and that was the correlation value. So if you try to plot the values that I have for xn over a time period, the graph looks like this, and this is just the first 50 values that they have plotted. And the correlation that we just looked at was for the 1000 values. But yeah, you see the point that what's happening is to determine, so let's say we started off here, and to determine what's going to happen next, there is a 50% dependence on the x minus, on the value that x took previously. But then it's not only that, there is some random error, some random fluctuation that I can have, which can take any value. Just we assume that it's not a bigger value, but it can also be a bigger value. So that's there. And if you want to have a look at this data, if you try to understand what's happening here, it really seems a bit of not really nice series, right? Because I don't know, should I connect these dots from here to there? Or it would take so much of time, right? So what you do is you try to connect all the dots, and then you have a line graph for this time series that you have. And now you can see that, you know, there are some regularities. Maybe it goes up, then for a while, and then again it goes up. So this looks like a bit of a random time series, but it is not quite that random as well, because we already know the function that we have, or the model that has derived this time series. But if you look at the graph, and if I try to chop it, there is not much of the same tendencies that I see in the graph, right? So that actually corresponds and actually corroborates the fact that we saw that, you know, after the lagged 2, there is not much correlation. So you cannot really predict what's going to happen next if you know something about the previous values. So that's there. Okay, and then this is the next kind of a series that you can have, which is the alternating series. So let's say if you have a higher value today, then there is a chance, a nice chance, that you will have a lower value some other day. So what's happening is, one day you start from here and you reach the top, but again you reach the bottom. So if you try to figure out the mean for this kind of a data, you know that the values will generally be one time above the mean and the other time below the mean. So that need not be the case always, but that is the case mostly. So we know that this is an altering time series. So now if I were to look at the correlation for this kind of a situation, then I would have a graph something like this for my autocorrelation. So for 0, I need to, you know, have the value 1, but then for the next time at 1, it's negative. And then again, it's positive, negative, and it goes on altering. So yeah, that is how it looks like. So generally what happens is you have the data, and what you will do is you can directly plot these kind of graphs, and this will help you to determine what's actually going on in the time series. And you can always plot these kind of graphs as well. So this is the very basic graph that if you feed in the data and you draw the, and you give plot function, it will give you the exact same data. Okay, and here the model that we were looking at was something like this. So we know that it's altering. Why? Because what we have was some negative coefficient for xn minus 1 here. So let's say I have my xn, we'll take the same example of minus 0.85 xn minus 1 plus an. So forget about that for a while, and let's just assume that this is the case. And what I can do next is minus 0.85, and I can again substitute in for xn minus 1, minus 0.85 xn minus 2, right? And that will just give me 0.85 square xn minus 2. So what we observe here is the relation between xn and xn minus 1 is negative. So we have a negative correlation value, but between xn and xn minus 2, there is a positive number that I have. So a positive correlation value, and that is how it keeps altering, and that is how your graph would look like. To be pedantic, Correlogram. Okay, so that was something alternate. And now we also have some series with a trend. So let's say the very nice example, the very first example that comes to my mind when I talk about a trend these days is only the number of coronavirus cases that are increasing in any particular country or in any particular region. So we see that there is an increasing trend. Okay, maybe this doesn't look like an exponential graph that we saw, but this is how it might look like given that, the recovery measures are being taken and people are getting recovered these days as well. So there can also be some trend where the long-term tendency of the data is to either increase in value or decrease in value, as and when you increase and as and when you look at more time periods. And that is all about the trend. So if you know that today the value is up here, then you know that it's going to be higher some other day and it's going to be even higher the other day. I mean, there will be some random fluctuations again because of this EN, but on an average, the tendency of this random variable is to increase in value over the time periods. And if you try to plot the correlation, you know that there will be a nice correlation, right, among this value and that value, and then this value and that value as well. So if you have a look at the correlogram, you see, right, even when you are looking at lag 10, there is not much decline in the correlation value. So we know that this is pretty nice correlation that is, being exhibited in the time series that we're looking at when it's trendy. And okay, so when you have, so this clearly is not declining at all easily and quickly. So it shows that, that this is a very strong trend because there is nice correlation even at lag 10 and lag 1 if you have a look at. But what can happen is sometimes the trend can be weaker as well, not as strong and not as prominent as always. And the value that you have, so let's say, if you have a look at the equation that we had previously, it was 0.1 n. So as and when you increase your n, the coefficient that was with n is 0.1. So it is more likely to be higher than if you look at here. So the coefficient of n is just 0.001. So it still is positively correlated, but the trend is much, much weaker. So if you have a look at the data, you cannot really see that there is any trend at all in this data, at a glance, if you don't know the model that it's following here. So if you have a look at the correlogram, it decays fairly quite easily, right? And quite quickly it has de-escalated to a very lower value. So that is what happens when you have such trendy data, but with weak tendencies. Okay, this is actually a very nice question. So let us try to figure out what will happen. So we looked at trendy data and we looked at, other data which is alternating and anything. So we also know that the other kind of data that we can always have a look at is seasonal data. So let's say if you look at the sales of Christmas trees, of course, during the times of November and October and December, it's going to be much more higher than the other times of the year. So every time the December, the October time comes, there will be a pick in the number of sales of the Christmas trees, right? So that's always going to happen. And even if you, let's say, look at the flood cycles for that matter, they sometimes have a tendency, in the rainy monsoon seasons, that chance of a flood occurrence is much more higher than in other months. So let us try to see what this question is asking us to do. So they're asking us to find a time series. Okay, so they are determined. So the variable into consideration here is the daytime temperature in months. And we know that, if it's winter, it's going to be a lower temperature, and if it's summer, it's going to be a higher temperature. And there is somewhat seasonality that we'll have to take into account in quarters. So what they have asked us to do is to sketch a diagram of the autocorrelation function of this series. Would you all like to try this on your own? How would the autocorrelation look like? So let me just, draw something. Okay, so let us say this is my plot. And this is the lag that I'm looking at. This will be my autocorrelation. Okay, and I have would anyone like to try this? Maybe I can allow you guys to, draw in here. Yeah, so you all can actually go to the annotate function and try to draw how would it look like. Let me see. And if you don't want to draw, you can just, discuss it among us. How do you think it should look like?
What is the scale of K? Days or?
What is the scale of K? Is that your question?
Yes.
Scale of
Is
K.
it
What do you?
5 days or 10 days? 5 months, 10 months?
Yeah. Okay. It's actually in months. So I'm considering months.
Okay.
Good question. Yeah. So these are the months. And let's say I have 1 here and -1 there. So we know that for 0, it's going to be what? 1 always, right? Now try to draw it for other values.
At 5, it would be negative.
What did you say? X5 will be negative.
Yes.
And why do you think so?
Because if we look at 6 months temperature wise, it's one season. If it's summer, then after 6 months, it will be winter.
Yeah, so let us say we are looking at, the 12-month period and we are looking at different quarters. So if I'm considering the correlation between the temperature in January and February, so that would be quite correlated, right? Not exactly correlated, but still there will be some correlation, right? And now if I go to March, there will still be some correlation, but not that quite. I mean, it would start, being hot. And then you look at another time. And then you can go and have some zero correlation as well. I mean, it doesn't matter. But we know that it's going to decrease after a while. But then there will come some time where it also starts to again increase. And you again have some zero. I'm just drawing this. Oh, I've already drawn 13 of these values. So I would see something like that. And once I have something like this cycle, I know this is going to repeat every 12 years in the same manner, right? So this is the seasonal kind of a data that I'm looking at. My drawing skills are bad. And that is what they have explained here. So you can have a look. And let's start with the next topic that we have. partial autocorrelation function. So we already have autocorrelation function. Why do you guys think there was a need to, even have something like partial autocorrelation function? Okay, let me maybe just define what is partial autocorrelation function, and then you guys would be, a better guess of why do we even need such sort of a function. Okay, so when I'm talking about the partial autocorrelation function, okay, so remember I can just, for this purposes, I'll write it as PACF. Even if you go and, do the R, you can always use ACF and your series, and it will plot you the covariance function, and if you use the autocorrelation, it will give you the Correlogram directly. We have nice libraries in our and nice packages. And time series is a really interesting topic. And let's look at partial autocorrelation function. So the symbol that I'm going to use to define partial autocorrelation function is phi. And again, it depends on what the value for my k is, where k can take any values from 1 till wherever it wants to. Okay, so when I talk about this, I can see that my partial autocorrelation function is a conditional correlation. So this is a conditional correlation of x t plus k. So this is the lag that I'm concerned with, and I'm figuring out the conditional correlation of x t plus k with x today, given the values of all of this interim x's, k minus 1. So what we do is, what we're trying to figure out when I say that I'm looking at the partial autocorrelation function, what I do is I assume and I do not take into consideration as random variables xt plus 1 up until xt plus k minus 1. So I assume that I know those values, and I take into consideration that these are the values which have in turn determined the value of xt plus k. And I only look at the correlation of xt and xt plus k. And this is actually, just the way. So if you would have studied economics, and just in case, even in statistics, the way you do linear regression, the way you determine the model. So let us say I have my xt, which depends on some random variables. So what I do is I try to minimize the error that I will encounter when I'm trying to model. So let's say if I have xt, and when I'm talking about partial autocorrelation function, it is actually a very nice thing which directly gives you the coefficient of the dependence between this random variable and that random variable. So I'm looking at this plus phi k comma 2 xt minus 2 plus some random variable e t. So let's say this is my model, and this is how I say, that my model is somewhat like. So I plot the covariances, and I'll explain later on how to determine how many lags you should have. But let's say, just assume that this is how I think my model should be. So when I'm doing out the regression, what I want is to minimize the value of the error that I have. So my main aim is to minimize ET. And when I'm talking about ET, you just try to square it for the same purposes as you cannot take the absolute, because it's tricky when you try to differentiate it. And if you just take expectation of ET, it is just, 0. So what I try to look at is expectation of ET square. And I want the average expected value of my error term to be as minimum as possible. So I just rearrange this equation, and what I get is expectation of xt minus phi k comma 1 xt minus 1 minus phi k comma 2 xt minus 2 squared, right? And this is now what I want to minimize. So what you do is you will use this expression and you will try to minimize, and that is what will give you the values of these parameters, which are the partial autocorrelations. So let us maybe try to determine. We have a nice question actually. Yeah. So this is the question. Try not to have a look. Oops. Yeah. Okay. So I have a process xt, which is 0.5 xt minus 2. So we don't have any xt minus 1. So we can assume that the coefficient that was for xt minus 1 was 0. So there is no relation between xt and xt minus 1. So if you know xt minus 1, it doesn't help you in any ways to know what's going to happen next, but it might help you to know what's going to happen next in the time which is next to next. So now I know that I have xt minus 2, 0.5 times xt minus 2 plus et, which defines my xt. And et is the error term which we assume follows white noise process. And remember, when I'm talking about white noise process, it doesn't always mean that the expectation is 0 until unless it is explicitly mentioned that the expectation is 0, which would always generally be the case in this chapter at least. Okay, so now what they are asking us to do is to determine the partial autocorrelation function for this process. And using what we just saw, what can you guys, say about the partial autocorrelation function of this particular process? So if I look at lag 1, so let us say if I'm looking at lag 1, what will be the value for the partial autocorrelation function? Anyone? And if I'm looking at lag 0, what will be the value? It will be 0, right? Doesn't really make any sense. Actually, this does not make sense. Forget about that. Yeah. So if I'm looking at lag 1, so I know that I'm looking at the partial autocorrelation between xt and xt minus 1. What would that be?
0.
And why do you think so?
Because there is no correlation between xt and xt minus 1.
Exactly right. So when I'm writing xt, I can clearly see in the equation itself that the values that my random variable take at time period t and at any time period which is next to t or prior to t is going to be independent of those. So the correlation is 0, which is also the value for the partial autocorrelation. Okay, so let's say now if I'm looking at lag 2, what will be the value for this case? Anyone? Already. So yeah. Anyone?
Is it the coefficient of xt minus 2 term?
Okay, so we don't know for sure, right? Let us try to have a look of what we studied for the partial autocorrelation function. So we saw that when I try to write my expression, I get something like, so I'm trying to minimize this term, and that is how you derive the coefficients. And the coefficients for each xt is the partial autocorrelation of that with respect to the xt, right? So here, you should definitely be sure that if I have 0.5 here, which is the coefficient of xt minus 2 there, then that is my partial autocorrelation value for the lag of 2. So the answer would just be 0.5. So the phi of 2 is nothing but just 0.5, right? And again, if you have a look for the other lagged values, we know that it doesn't show up in the equation just as xt minus 1. So again, for the rest of those values, the value will be 0 for partial autocorrelation. Does this make sense to everyone? This is really an important concept, and you can ask me any doubt if you haven't understood anything, or if you still have some doubts here and there. Does anyone have any doubts up until now? If you don't have any doubts, say no, at least.
No.
Ma'am, what is that
No,
phi 2
ma'am.
comma 1 and phi 2 comma 2?
What is that 5, 2, comma 1 and 5, 2, comma 2? Okay, that is just a way to write the coefficients. So if you have a look here, what we did was we wrote 5 k comma 1, right? So if you are looking at t minus 1 and if you're looking at t minus 2, so this is just the 2 that you have, and k denotes the lag that you have. So this k is actually constant everywhere. So, okay, let me maybe write. So if you are trying to determine the correlation between xt and xt plus k, so this is the k that you have, and that will always be here. And if you have t minus 1, so 1 and 2 and k again there. Does that make sense?
Yes, got it.
Okay. Any doubt? But you don't have to use that complicated notation, just write this in short, phi of 2. I mean, it's clear that we're looking at 2. It doesn't matter. Okay, so maybe I can show that. Yeah, so this is how the ACF, so I haven't yet told you guys what ARMA and this 1, 1 means, but just assume that this is some sort of a model, okay? This is some sort of a model where my xt depends on one lagged value of itself and one lagged value of the error. And that is how I write for ARMA 1, 1. Okay, maybe we should try to look at the main models. So there are some general models that we have in time series, and they are of 3 kinds. One is autoregressive, other one is moving average process, and the third one is autoregressive moving average process, which is ARMA. So AR, MA, and ARMA. And when I'm talking about autoregressive, you must have already heard the term regression, right? And when I'm talking about regressive, what do you guys think it could be? You know, we just talked about autocovariance, autocorrelation, and now I have a model which is called autoregressive. So when I'm talking about a model which is an autoregressive kind of a process, what I'm trying to say is that it depends on its own values, which are lagged by some certain time values. So if I were to, maybe I should just write this. Okay, so we have three different kind of linear time series models, and mind you, we are talking about linear time series models because there is like a whole another nice concept of non-linear time series models, which is, I would say, much more beautiful than the time series models, for me at least. And that is mostly used in case of weather and politics as well. So you try to use these time series concepts in political scenarios as well. There's a wide application because even though there are certain qualitative aspects to it which you cannot measure, there is some way wherein you can, rank them or sometimes have some qualitative data as well. So let us talk about the linear time series models which we have to care about. Has anyone heard of chaos theory before? So remember the IAI's day, sorry, the Actuarial's day, which was celebrated on 21st. This time, the chief guest was Sanjeev Sanyal, right? And he's actually he's actually a very famous economist, and I especially admire him for the work that he has done in chaos theory. And there is a nice concept known as butterfly effect. You might have heard of the movie, The Butterfly Effect, or just some Instagram posts that do come up about the butterfly effect. And that just says that, if a butterfly flaps its wings, let's say in Kerala, then that might cause a storm in West Bengal. So it just says that even if there is some small change in the initial condition, it might lead to a drastic change in the actual outcome or the behavior that you observe. And that is generally seen in the case of non-linear time series, not in the case of linear time series. It's a really beautiful concept and a really beautiful subject of chaos theory that I have had a chance to study from a very nice person as well. So, wow, I am very, so let me just concentrate on what we have. So we have autoregressive processes, autoregressive process. And when I try to define my autoregressive process, I can say that these are the kind of models where if I try to forecast a future value, that will be based on its immediate past values within the same series. So if I were to write the model for this, it would be something like xt equal to mu plus alpha 1 xt minus 1 minus mu plus alpha 2 xt minus 2 minus mu plus alpha p. I'll tell you what this reference for p is and the error term. Okay, so the process that I have written here is an so this is actually a ARP process. So this is the order of my AR process. And when I say that my order is P, I know that my value depends on immediate P values. So T minus 1, T minus 2 till T minus P. So these are the P values of X that my random variable xt depends on, and the error term is only for today. So there is no error term from the past or its immediate past as well that we are looking at. So these kind of processes, these kind of models are categorized into autoregressive models. And when I'm talking about next, let's say moving average models. So we'll deep dive into these models soon. And before that, let me just, write in short how these models are. So yeah, the first kind was AR. And now we'll have a look at the moving average processes. And when I talk about moving average processes, what happens is my future values will depend only on the past values of the error, not the random variable itself. So if I were to write the model, what I will have here is my xt depending. So this is the mean that I have, and this is the error term for t, which is today, which I always have in any model. And now the extra dependency that I have is not in between these variables, but in et minus 1. So there will also be some coefficients again here. So let's say beta 1, et minus 1, up until beta q e t minus q. So I have till t minus q here. So I say that this is a moving average process of order q. So here we had looked at the data until t minus t. So we say that my random variable depends on its immediate p values, which is why it's autoregressive of order p. Here the errors that determine my t value are from t till t minus q. So I have MLQ process. And MA processes are always stationary, right? So if you have a look, the expectations, these are supposed to be white noise with mean 0 as well. So the mean will be constant, the variance will also be constant, and the covariances also satisfy all the properties of stationarity. So the moving average models are normally always stationary in nature. And there is a nice connection between these AR models and MA models, where if you try to substitute the values of X again and again and again, you kind of can come up with the moving average model of the same thing. We'll have a look at that as well. And I think by now you must have guessed if I'm talking about the third model, that is ARMA model. So for MA, we look at the Q. For AR, we look at P. And for ARMA, we look at P, Q. So what we have is a mixture of this and that. So my XT will depend on its lagged values of X as well as the lagged values of the error terms. So I'll have something like mu plus alpha 1 XT minus 1 minus mu plus alpha P XT minus P minus mu plus ET. So this is the part that I got from my AR model. And now will be the part that I get from my MA model. So beta 1 ET minus 1 up until beta Q ET minus Q. And that is how you get your ARMA model. And the value of P and Q is the ones that you have here. So if I were to write my AR model and MA model in terms of ARMA, what I can do is I can actually write my ARMA for some values, and ARMA for some values is just equal to ARP, and this is equal to MAQ. So when my P is 0 and I have this Q, and if I have this P and my Q is 0, I know that I can rewrite my AR and MA models as in terms of ARMA models with respective other quantities which we don't see as 0. Is that clear to everyone?
Yes, ma'am.
Okay, so I think I'll just end my class today here because then we'll be starting off with. Do you guys mind if I take 10 minutes more? Okay, I'll consider that as a no. So let me just start off with. This is a really small concept. I'll just cover it in 5 minutes. Just give me 5 minutes. I started the class 5 minutes late, so I have that excuse. So this is something known as backwards shift operator. And I denote it as B. And then there is something else known as difference operator. And this I denote by not B, but delta. That looks like pizza piece, but yeah, delta. Whenever I see delta, it always reminds me of pizza. But I think that's the best part of at least, studying this. Anyways, so when I'm talking about this backwards shift operator, what it does is, let's say if I have a process xt, and if I apply this backward shift operator, so consider this as just some function. So and other times I define my f of x is this, right? And I'll say my f of x is, let's say, x squared. So this is just some operator function that I can apply on my variable xt that I have. So if I write my b xt, and I can rewrite it as this. Oops. The first bracket should be there, and I really hate the way, we have this brackets. I mean, I always want this t to be inside the bracket and this b to be outside the bracket, but that's just how they have given it in the book. So let's just stick to that. So if I apply my backwards shift operator on this process x, at which we are observing at time t, what it will do is it will give me the value of x at one time period backwards. So if I'm looking at xt, if I go one step back, it will be xt minus 1. So if I'm writing bxt, it will just be xt minus 1, right? And let us say if I have this, let's say this is 1, 2, 3, simple. This is time t, this is time t plus 1, this is time t plus 2. Okay, and my value at time t is this 1, and this is that, and here we have 3. Very easy, right? So if I'm applying bxt, and if I'm using this, what should be my value? If I say that my t here is 2, what should be the value that I get here?
X1.
Assuming that I'm looking. What should it be?
X1.
X1.
X1, right? So it should be X1. And let us say if, so it should be X1. And just say that this is 0, this is 1, and this is 2. So the value will be 2, right? And let us say another model that I'm looking at takes the same value everywhere. It just takes the same value everywhere. And now if I'm looking at bxt, when my t is 2, what will be the value now? It will again be x1, and the value for x1 is what? Again 2. So let us say if I apply my backwards shift operator to a constant number, which is u, right, at some time. So I know that my constant, if I'm looking at a constant variable, it is going to take the same value at each interval of time, right? So what I'll have is, irrespective of how many times I apply backward shift operator, I will always get the same number as my output. Does that make sense?
Yes.
Good. Okay, so that was about backward shift operator, and you can also use b square. So if for bxt you get xt minus 1, then you can apply b square, and if you apply b again here and b again there, so you will get bxt minus 1, which will be xt minus 2. So let me just, and now we look at the delta. Okay, so when I talk about difference operator, I can rewrite my difference operator as 1 minus my backward shift operator. In other words, I think this is not much intuitive, but let's say if I write this and x and t here. So remember when we talk about partial derivatives, we look at, the change in the random variables, the change. So this is somewhat like that, and this is just the, so if I try to write this delta times xt, this will be xt minus 1. So remember what happened with b was you just shift one place backward. But here when you're looking at the change, it gives you the incremental value in xt from xt minus 1. Does this make sense?
Yes.
So when I say that my delta is just 1 minus b, so I can rewrite, instead of this delta, let's say I write 1 minus b x t. What will that be? I get x minus b x t, right? And that would just be xt minus b x t. And I know what is my b x t? xt minus 1, right? So which is why this delta is in essence equal to 1 minus the backward shift operator. This is equal to 1 minus b operator. Okay, and there are other operations that you can again do on these things. So let me create some space. Okay, so I talked about, b square x t. So if I were to figure out the value for this, I can just rewrite it as bbxt. And I know my bxt is what? It is just x of t minus 1. So this will be my bx t minus 1. And again, if I apply the backward shift operator at time t minus 1, what I get is t minus 2. So when I have b square, so whatever the number that I have here is the number of places I go backwards in time to have a look at. And let us say if I'm looking at delta squared x t. So what you can do is, you can again write this value. So you can either substitute this 1 minus b here. So let us just do that because I find that case very easy. So if you can just, we know that this delta value is 1 minus b. So I can just write 1 minus b square x t. And I can expand this 1 minus b square, which will be what? 1 minus 2b plus b squared. Oops. Yeah. xt. And then for x, you only have xt. And then for here, you will have minus 2bxt. So maybe just, for now I write this plus b square x t, right? So what you get at the end is xt minus 2. bxt will be what?
xt minus 1.
Yeah. And what will be b square xt?
xt minus 2.
Perfect. xt minus 2, right? Good. So we can again solve this using some another method. So let us try to do that. So when I say that, I'm looking at this square xt. So instead of substituting this backwards shift operator, I can actually apply the delta first. So what I'm in essence saying is that I'm applying delta to delta x t, right? So what will I get is delta xt minus delta x t minus 1, right? Because I have applied delta to delta xt. So I get delta xt minus delta x t minus 1. And if I were to expand that, so delta xt is what? Xt minus 1. And my delta xt minus 1 is what? Xt minus 1 minus xt minus 2. So minus xt minus 1 plus xt minus 2, which is exactly the same thing that we had, right? So these are two different methods in which you can, do these things. And remember, for every type that you have for B and for delta, if you have square, you can always expand it as 1 minus B square. And if you have cube, you can expand it as 1 minus B cube. And then write down the whole cubic expression and solve for the x value that you have. So we introduced this B concept and this delta concept just to make our lives easier and have a smart way to write this model instead of, getting bogged down with t minus 2, t minus 3 always. So you can just write it as bxt, which will be xt minus 1. So that is where these expressions will come in handy. And in next lecture, we will try to discuss all of these models in detail. And I will put it in the group when that lecture will be. So I think probably the first lecture that we will have will discuss some sums from the copula chapter for the initial half an hour or 1 hour. And then we'll start off with the time series. Otherwise, I can maybe actually, because you guys have exams, if you all, it's up to you guys, what do you guys say about this? So what I was trying to see is if you can solve the copula practice questions from the back of the chapter on your own and see if you can solve those, because we have actually, studied the questions that we had in between the chapters. So I think you guys have some idea more or less of how to solve for the practice questions as well, even though we haven't yet solved any exam style question. But I think it should be fairly similar. And if you guys can try that on your own and just ask me doubts if you have any, so that, the next lecture, we can actually utilize the whole 2 hours just to study the time series. What do you guys suggest?
Yes, ma'am, we'll do it on our own.
What about others? It's okay if you need me. I'm there also.
Yes, we can try.
Yeah, so what I'm saying is just try it out and put it in the group if you have any doubts. So I can always try to explain there. And maybe if you put questions in the group, it might motivate others to study as well. So yeah, we can have something like that.